We're going to wait on a few more participants and we'll get started in a couple of minutes, guys. All right, guys, we're going to go ahead and get started. A little bit about last week. I hope the exam went well. We introduced the concept of derivatives and rates of change, so we're not going to talk too much about the conceptual backing to derivatives today, but we are going to focus quite a bit on symbolic manipulation and cranking through problems. So we're going to introduce the power rule, product rule, quotient rule. We will do some limit evaluations, and we'll do some trigonometric examples as well. So I'm going to get my screencast going and we will dive in. Okay. So first thing that I mentioned is to refer to figure 6, page 140. So that page number is from the physical textbook. And if you don't have the physical textbook, it'll be in section 2.3. And figure 6 has the pertinent derivative formulas for the first two problems that we're going to do. It does not include the formulas that you need to know for trig derivatives, and I don't give a figure or a page number for reference for those, but I will go over the ones that you should have memorized or in your back pocket as we get to that later in the lesson. To start, I guess we'll just introduce the power rule and the product, or yeah, the power and the product rule. So this problem here, number 25, you have the option to do it one of two ways, with the power rule or the product rule. If you were to use the product rule, which the product rule is, so if a product is something that you get when you multiply two numbers. So the product rule goes for when you have two things that could be functions on their own that are being multiplied. Quotient rule for when you have a quotient, something that's being divided. And then the power rule for when you have a function with a power in the superscript like this. So I decided to do this problem with the product rule because, or excuse me, the power rule, because I think the power rule is just so much easy. There's less factors. I don't know if factors is the best word in this case, but there are less terms. And so what I decided to do was to use algebra first and to FOIL it out and to get each of those terms independent so that I could do the power rule on each one. You could have decided to combine these like terms before. I decided to do it after. But the way that the power rule looks is basically you drop the exponent and you multiply it by the coefficient, if any. If there's not, then the coefficient is 1. And then you're going to reduce the power by 1. So this is going to end up being 5 times 5 times x to the 4th, so 25x to the 4th. This one here, we drop the 3, it would become negative 6x squared. This one becomes positive 45x squared. And then whenever you have a linear function, whenever you'd have just the single x with no power, technically it does have a power, as a power of 1, and the power rule still applies in this case. You can reduce the power by 1, but you're reducing it to 0, and anything to the 0th power is just equal to 1, so it ends up being negative 6 times 1. You'll come to find that you can apply these differentiation rules to some of the simpler parts of the derivative that you'll have to take, but there's really no need to. What I mean by that is technically the power rule can be applied here, but there's no reason to go and think through it all, because you know, like based off of what a linear function looks like, you can pretty much picture that the slope is going to look like negative 6, because there's no, if we were to focus only on this part here, it would just look like -6, no intercept, and the intercept really wouldn't make a difference anyways because coefficients or constants, excuse me, have a derivative of 0 anyways. And so you don't really have to do much thinking for these linear aspects of derivatives when you are taking derivatives of polynomials. And then for the final step, I combine like terms. I'm going to talk a bit. You'll notice throughout my lesson today that I don't combine like terms for the majority, or I don't simplify my answers for the majority of these problems. And the reason for that is something that I've mentioned before. And it's that once you've done the calculus on a problem, say you're on an exam and they ask you to take the derivative of something, you're being tested on your ability to take a derivative, not to combine like terms to simplify whatever. If the problem requires you to do that before you take the derivative, then yes, you are being tested on that. But once you've taken the derivative, if you were to simplify it thereafter, you'd A, be wasting your time, B, giving yourself more of a possibility for making mistakes the longer you work on it, because you're not going to get marked down for not simplifying your answers unless the problem asks you to. You won't get marked down for not simplifying, but you will get marked down for simplifying incorrectly. And so you'll see that I don't often simplify these answers. Also, because we've got a lot of problems to get through and I didn't think it was a good use of time. And again, it doesn't matter if you would prefer to do it that way, because I've noticed that some students, they get a better grasp of whether or not their answer is right or wrong if they decide to work it, if they work it out. But that's why I don't simplify my answers on this. But for the odd numbers, as always, you can find them in the book. And if you were interested to know what the simplifications look like, you could always shoot me an email and I could let you know. Also, I will stop and ask questions, ask if there are questions throughout the lesson. I don't expect a lot of questions to come up today. There weren't many in the first recitation. That being said, I am going to stop and give you guys an opportunity. But if I don't stop frequently enough, as always, please stop me and let me know. All right, so this next one is a surefire product rule one. You could try and FOIL this out and combine those terms, but all of these have different powers, so it would just end up, it's simpler to just go about it as though it's the product rule, which it is. The important thing to note about this problem is that we have these powers in the denominator. And so what we're going to have to do is some power manipulations. We're going to have to take these, excuse me, these variables and put them up top so that we get them all in the same form. You could just FOIL it out as is and get some fractions, but then you're going to have to do the quotient rule multiple times. And so I would say that it's simplest just to put these powers up, and remember inverses is this, remember the relationship of an inverse because it's going to come up. But the negative power is representative of an inverse, and then 1 over something is representative of an inverse. When we talk about trig, it'll be arc, or there's another term as well, but I won't get too much into the trig for now. But once we have done that and we've put our variables into a workable form for us, now we can go about doing the product rule. And so, like I say, with a lot of calculus, it's very important to kind of break this down in English in your mind. And that's how I'm able to remember these formulas from when I learned them junior year without referring back to the book. Because in my head, every time I say the derivative of the first times the second plus the first times the derivative of the second, I kind of switch up a little bit. And when I write out the actual answers, I've noticed when I was teaching earlier that I didn't always put them in the order that I recommend to you guys to do. But for me, I've been doing this for so long that I'm able to track that. For you guys, if you're just starting out and you don't have any prerequisite knowledge on taking derivatives, I would recommend trying to stick to that pattern every time so that you can get it to become second nature, because these differentiation techniques are going to be one of the bigger skills that we carry throughout the semester. And calculus is a very cumulative subject. So I would make sure that you have these down pat. And so we're going to go about doing the product rule. So it becomes the derivative of the first. We're going to do the power rule to find the derivative of the first. So we're going to drop that power and reduce the power up top by 1. Do it for both terms. So derivative of the first times the second plus the first times the derivative of the second. Does anyone need further explanation on how to do the power rule for these problems? Please let me know now if you do. Okay, because otherwise it's the same thing over and over again, and I won't explain it going forward if people don't have questions. I will here and there, but I won't explain every single term per se. Okay, and like I said, if I were grading the exam, and Dr. Zalecki and I have graded exams together before, and he has never had an issue with the way that I've done it, I would give this full credit. I would not expect you to try and combine like terms with this. It just looks chaotic. I wouldn't even want to attempt that myself, because if the problem is only asking you to find the derivative, you've done that. This is a workable form. Say they were asking you, so we will do problems towards the end of or about halfway through the lesson where we're asked to find a tangent line. In a case like that where you're asked to find, so in order to find the tangent line, we have to find the derivative first. In a case like that where finding the derivative is just an intermediate step to our final answer, you may have to simplify. But if the problem is just asking you to find the derivative, then this is an answer that I would give full credit to on an exam. Moving on to the next one, introducing the quotient rule. So we know this is the quotient rule because we have a function on top and a function on bottom. Say there weren't a function up here and it was just 1 over 3 minus 4x. Then what we could do is we could say in parentheses, it's actually 3 minus 4x to the negative first. And then we could do the power rule on that as a whole, but that's actually, don't worry too much about that example because what we haven't introduced yet is the chain rule, and that gets into the chain rule. So forget what I mentioned there about this possibly being a 1 over situation. Let's just focus on what it is. So we've got a function up top and we've got a function up bottom or on bottom. And so what we're going to do is we're going to do the derivative of the first times the second minus the first times the derivative of the second divided by the second squared. Some people say top and bottom, whatever it is. I just think it's very important to get into a habit and to kind of establish that pattern so that when you're on an exam and you're cranking through the problems, you don't have to worry about the technique. You can focus on the question and the concepts being asked specifically for that problem. So the way this looks is derivative of the first. Constants don't have derivatives. The derivative of a 2x linear function is just 2 times the second minus the first times the derivative of the second. So this is what I was talking about, how I kind of flip-flopped them. I wish that I had them the other way around so that it fit the way that I have this formula memorized in my head, but it's not that big a deal. It's not like you're going to get marks down for the order in which you multiply. And then all over the bottom squared. And again, this is a perfectly fine final answer. Anyone have any questions before I move on? Okay.
I have a quick question, actually.
Yeah.
Wouldn't the derivative be -4 of the bottom?
Yes, it would.
Okay.
Thank you.
Yeah.
So, and then, okay, now this is a perfectly acceptable answer. Thank you. Nice catch.
Yeah.
Okay. So now, moving on to number 31, we have another quotient rule example, straightforward. We use the power rule to find the derivative of the top times the bottom minus the top times the derivative of the bottom. And again, this is just using the power rule, but the power rule is a part of the quotient rule in this case. The larger formula that you're going to apply is the quotient rule, but within the quotient rule itself requires you to find the derivative of both aspects. And so how are we going to do that? We're going to use the power rule. Okay. Next one. So I have noticed that some students will see this and they'll think, okay, can I factor this? Because we have done a lot of examples up until this point where we have tried to rationalize things and cancel with the bottom to try and make our limits evaluatable. But we don't need to worry about that when we're taking a derivative. They're not asking us about rationality or anything like, or continuity or holes or anything like that. We only care about the derivative. And so that's really the only thing I wanted to mention, because I've noticed that some students will kind of fixate on the fact that this might be factorable and you might be able to factor something from the numerator. Yeah, that might be possible, but ultimately you're just giving yourself more work because you can plug this straight into the formula as is. And so when we do that, it looks like this: derivative of the first times the second minus the first times the derivative of the second, and all over the second squared. And it's becomes the same thing. This will start to get repetitive, which is why I said that there weren't many questions in the first recitation, because there's really not a whole lot to be asked about the application of formulas. But we will do some problems that are a little bit more of thinkers, but for now it gets kind of repetitive. So moving on to number 35, this is an example of a problem that you would have to do an algebraic manipulation to beforehand, because this is going to have to be a power rule problem. The reason being that this has a power of 1/2. And so you're going to have to manipulate it into its fractional form of the power first in order to be able to reduce the power and drop the power out front. So it looks like this. And then when we plug it into the formula, we get the derivative of the first. So the derivative of s is just 1 minus, we're going to drop the 1/2 down in front, and then 1/2 minus 1 is -1/2 times the second minus the first times the derivative of the second. This looks like 25, but it's 2s over s squared. Any questions on converting to fractional powers? We will do one more example on that, but does anyone have any questions on how you arrive at that? No? Okay, another example. So since this is not the square root, it's a cube root, it's going to be the 1/3 power. You're going to go about it exactly the same as we did the last one. Derivative of the first, we're going to drop the 1/3, and then 1/3 minus 1 is -2/3 times the second minus the first times the derivative of the second over the second squared. I do want to mention that some students have difficulty with not necessarily, maybe they are able to convert into the fractional power, but then when it comes to subtracting 1, for some reason, students will get tripped up. And so if you find yourself maybe making these mistakes on your homework assignments, I think it would be perfectly reasonable to go over on the side and say, okay, actually, that's not what I wanted to do. Say that it was the 1/3 power, to say 1/3 minus 3/3 is equal to 2/3. I think that I don't feel the need to write that actually. But I used to do that when I was taking my exams, and I was getting, just because when you get into these higher level problems and it's a lot of cumulative material, you don't want to be worrying about whether or not something small like that is going to affect your answer, and whether or not you're going to have to go back and find those types of mistakes. So it's perfectly reasonable to write out simple things like that on the side if you find yourself making mistakes when you're practicing on your homework. Because I've noticed that a handful of students every semester that I've taught has had an issue, maybe not with the 1/2 power, but for whatever reason, when you subtract 1 from 1/3, I've noticed that some students will lose points on that. So yeah, that's enough on that. Moving on to the next problem. So this is, yet again, another quotient rule example. So it becomes the derivative of the first using the power rule. In each case, technically we're using the power rule for this one, but it's just a linear function, and so we know that the slope is just going to be its coefficient. Derivative of the first times the second minus the first times the derivative of the second over the second squared, and that's that. And those are all of the examples that we have for product rule, quotient rule, and power rule. Not that we won't use them when we're doing the trig examples, but this is, so far, if you have a grasp on what's been introduced today, then you're doing well with derivatives. So now what we're going to do is an application problem. And this is an integral question to the course Calc 1, and it will come up again and again. And the large concept to note here is knowing what a tangent line is and what is required to find it. And a tangent line, say we have the function x squared. The tangent line at any given point, it doesn't matter where, the tangent line just kisses the graph at one point. In this case, we want to find the tangent line that touches the graph at 1, 1. And since, I guess what I'm trying to say is this is the instantaneous slope. And when you're asked to find the tangent line, that means find the instantaneous slope. What's the instant? The instant is the point given. And to do that, we really only do one round of calculus. We take the derivative, and then from there, it becomes prerequisite information that you might have learned in algebra or pre-algebra. We're just going to use the linear function formula. And so basically, when you see tangent line, think instantaneous rate of change. Yes, it is an estimate, because at any given point, as you get further along the curve, it's going to become more and more steep. So it's not this. So the difference between the derivatives we've been taking up here, these are general derivatives. Now we are finding the specific derivative at one specific point. So a tangent line is supposed to be an estimate of the derivative at a certain point. But since we're using the formula to do so, it is accurate. So what we're going to do is we're going to take the derivative. Oh, no, I skipped a step. So you can use slope-intercept form, which is the y equals mx plus b, which is what we're used to seeing when we were in high school or in pre-algebra, if you took that last semester or last year, something like that. But this form you will come to find is a lot easier, because when you do y equals mx plus b, that b is a composite of both the x1 and the y1 variables. And like I've mentioned before, it's always simpler, just to go the simpler route is going to give you less opportunity to make mistakes. And for this, you just have to plug straight in. When we plug in, the x value is going to go here, so this is going to be 1, and the y value is going to go here, and that's going to be 1. So it's going to be y minus 1 equals the slope, m, times x minus 1. And how do we find the slope? We take the derivative of the general. So we're going to find the general derivative first of the general function, and then we're going to plug in our 1, 1, or just the x value 1, in order to find the specific derivative that we're being asked about. So how does that look? We have the derivative of the first times the second minus the first times the derivative of the second, which when we simplify, we get 2x plus 2 minus 2x, which just ends up being 2 over x plus 1 squared. You could have FOILed this out on the bottom, really doesn't make a difference. You're just going to end up plugging in anyways. Excuse me. So we're going to plug in 1 into that x in the denominator, and it becomes 1 over 2 squared, which is 1 over 4, which is 1/2. And that's our m value, that's our slope. And so we can plug that right into the function, or into the formula that I mentioned before, and we get y minus 1 equals 1/2 x minus 1. And that's how you do these problems every single time. These are the type I mentioned. There's a handful of problems. There's actually a lot of problems throughout calc that they'll be the same every time that you do them. And I want you guys to get those points, because there are going to be problems that you maybe haven't seen before, and you're expected to use your intuition and sort of piece them together. This is not one of those. This is going to be the same every time in the way that you go about it. You find the derivative at the instant that they tell you to ask for, or that they tell you to find it for, and then you plug in the values, and that's that. This should be one of the so it's new to you, and if it's not clicking quite yet, that's fine. But when it comes to the exam, this is the type of problem that I would expect you guys to get right every time, because this is A, something we've introduced early in the semester, so you'll have had more time to wrap your brain around it, and B, it's going to be one of those canned problems that looks the same every time. And so if you've done your practice, you'll know how to do it every single time. So now we're going to find the tangent line and the normal line. So I'll get to the normal line after we go about finding the tangent line. But again, it's the same thing as last time. We're going to have to find the derivative of the general function that we're given. So you should see this right here, of this square root, and think, okay, I have to convert that to its fractional power. And that is going to look like x plus x to the 1/2. So that when we take the derivative, we're going to drop that 1/2 and reduce the power by 1. And then we're going to plug in x equal to 1 to find what the specific derivative is at that point. So it ends up being 1 plus 1/2 times 1 to the negative 1/2. 1 to any power, doesn't matter what it is always going to be 1. So it's 1 plus 1/2, which is 3/2, which is the slope of the tangent line. And so when we plug in, we do y minus y1 equals the slope times x minus x1. So there's the tangent line. It's the exact same as the last problem, like I told you guys. Now we're asked about the normal line. So the tangent line is something that has come up in every single semester of calculus that I've ever taught. The normal line is something that I learned about in high school, and it's been brought up twice out of the semesters that I have taught. So since it's been brought up today, I think that there's a good chance that it'll be on your exam. But there's really not a whole lot more to learn once you've learned how to find the tangent line. The difference between the tangent line and the normal line is really not that hard to wrap your head around. So here's our tangent line. It's our instantaneous rate of change. It's kissing up right against the graph. And at that exact same point, the normal line will be normal to it. It will be perpendicular and have, so since it's perpendicular, a perpendicular line, if you remember from algebra, will have the inverse slope times -1, negative inverse slope. And so it looks like this. I don't like the way that I worded that, so I'm going to reword that before I send the note out later today. But basically, you just flip the fraction and you multiply by -1. If the slope was 1 originally, then it would be -1 for the normal line. So if the slope of the tangent line was +1, it would then become -1 for the normal line. And so if you've got a wrap on, or you've got your head wrapped around the tangent line, all you got to do to do the normal line is remember that it's just the inverse negative. The slope is the inverse negative of the tangent line. And then other than that, it's the exact same thing. Okay. Any questions on these, on finding the tangent or the normal line before we move on to trig examples?
with the example of the normal line, you have y minus 1 equals the negative 2/3. Shouldn't that be y minus 2?
One, oh, with x, you mean?
No, on the, because on for the tangent line, it's y minus 2. And then the normal line, shouldn't that also be y minus 2?
Yes, so they're flip-flop. I see what you mean. Thank you. Like that?
Yep.
All right, cool. Thank you very much. Okay, so no questions conceptually on how to do these though? If not, awesome. Okay, we will move on then. So now we're getting into differentiation of trigonometric functions. And off the bat, I see two aspects of this function. I see the x squared, which is reminiscent of polynomials, which we've been working with. And then I see the sine x. So basically what that means is I have two functions that could stand alone being multiplied together. And so I'm going to have to use the product rule, but then also trig. So like how when we would do the quotient or the product rule before, and I'd say, okay, yes, the larger concept here, the larger formula that we're adhering to is the product or the quotient rule, but within that, it's still asking for the derivative. So derivative of the first times the second, blah, blah, blah. It's still asking for the derivative. And so for polynomials, more often than not, that's going to be using the power rule. For trig functions, you have to use the trig differentiation formulas. And so this is something that I did not write down, but I will tell you guys sort of like a running list of things that I think you should be familiar with and have memorized for these types of problems. So first and foremost being that you need to know what the derivative of sine, cosine, and tangent are. So the derivative of sine is cosine, the derivative of cosine is negative sine, and the derivative of tangent is secant squared of whatever the variable is. So if it's sine x, sine theta, whatever. So looking at this problem, we're going to use the product rule. It's going to be the derivative of the first, which is going to be 2x times the second, sine x, plus the first, x squared, times the derivative of the second, which is going to be cosine x. So 2x times sine x plus x squared cosine x. And again, no simplification necessary unless you're being asked to find another answer beyond just finding what the derivative is. That's no different for the trig problems. There's really not much simplification you can do when it comes to multiplying polynomials and trig problems. So moving on to the next one, we have an example of the product rule here because we have the linear function x and the trig function cosine of x. And then we have a problem that, yes, we could use the product rule on. We could do the derivative of the first times the second plus the first times the derivative of the second. But the derivative of the first of the coefficient 2 is just 0. And so we would end up canceling that term. And so we'll come to find, here, I'll get to that in a second. So we have the derivative of the first times the second plus the first times the derivative of the second. And then you'll come to find with any of these functions that just has a constant out front, it's just the derivative of the function times its coefficient, times its constant. So the derivative of tangent x is secant squared x, and that 2 only serves to multiply with it, basically. And if you really wanted to, you could write out the product rule, and you'll find the answer is exactly the same, and you could do that on the exam too. It's just sort of a waste of time the more that you do these problems and the more of a grasp you get for the pattern of things. Okay, so other things that you should have in your back pocket, you should also be familiar with the derivatives of the inverse trig functions. So I want to say technically it goes both ways. So I believe it's, so cotangent and tangent are inverses. Technically, cotangent is the inverse of tangent, and also tangent is the inverse of cotangent because it goes both ways. It's just to the negative first. It goes back and forth. So be familiar with that concept, A. Be familiar with what the derivatives of cotangent, cosine, and cosecant are, and we'll do some examples on those as well. And then as the third thing, so far we've talked about the original, I say original and I do air quotes because technically the inverses are inverses to each other. It's just we're used to seeing sine, cosine, and tangent the most, but you need to know those derivatives, the inverse or the derivatives of their inverse counterparts. And then you need to know the relationship between each one. So we'll do some problems where we're asked to prove that one derivative is equal to something, and we'll need to know that the inverse of cotangent is equal to, and that tangent is equal to sine over cosine, things like that. So we'll do more examples, but those are kind of the three large areas that you need to have memorized in order to do these problems well on an exam. So looking at this, we get that the derivative, so again, like with this problem up here, we're just multiplying by a coefficient. So we can just pull the 3 out front and multiply it by the derivative of cotangent of x, which is negative cosecant squared, which makes sense because the derivative of tangent is secant squared. So the derivative of cotangent is cosecant squared, negative cosecant squared. Which you will come, like, again, like I've said, you will come to pick up the pattern and the similarities between these, and it'll become a little less memorization and a little bit more familiar, like it just being familiar to you. But moving on to the next one, same situation, we've got a constant out front. So it's -2 multiplying by the constant, and then the derivative of cosine is negative sine x, and that is a perfectly fine final answer. I just I don't know, personally, I would probably pull the negatives out when I was finishing this problem, but as a grader, I would not necessarily take points away for not pulling the negatives out. It just looks funky to me as someone with math experience. But like I said, this would still get you full credit. Okay, so for this next one, it's not going to be typical for you to see c cosine t. This is sort of an atypical representation of the constant, and that's what this is they want you to recognize that this is a coefficient, this is a constant here, and they want you to think conceptually without having an integer being there. They want you to think, okay, how would I treat a constant in this case? And so I think that's what I wrote here. Yep, c equals constant in this case. And so it's going to be the derivative of the first times the second, but the first has a derivative of 0, so you can just forget about it, basically. So it's like how we did with these examples up here and with the tangent example above. It's just the constant times the derivative of the trig function. And that works for other functions that we'll see in the future as well. So constant times the derivative of cosine t, which is negative sine t. And then we can do the product rule for the second part here. We get the derivative of the first times the second, plus the first times the derivative of the second. Any questions on that constant business? Or at all in general? No? Okay. All right, so next one is an example of quotient rule again. So we have got the derivative of the first times the second, excuse me, minus the first times the derivative of the second. And we got this negative out front, again, because we have this negative coefficient here, -1, and we maintain that when we take our derivative, all over the bottom squared. And there's not a whole lot of explanation. Once you've explained how to plug into a formula, there's really not a whole lot of teaching that's left to be done. So we'll move on to the next one. Here's an example of a problem that uses theta rather than x. We are pretty used to seeing x, but you'll come to find that in the story problems that we do going forward, you don't see x used as often. Theta is the most common variable used when referring to angles. And sine and cosine are all about angles. Think unit circle, think special right triangles, and we'll talk about those more in a second. But basically, I threw this one in here to get you guys familiar with it. But it's going to be another example of the quotient rule. We're going to have the derivative of the first times the second minus the first times the derivative of the second over the second squared. And it's the exact same thing we've been doing over and over again. And if you guys have noticed, I say it exactly the same time every single time I do it. And I do that when I'm writing my lesson plan alone too. In my head, I'm not saying it out loud. But every single time I write these problems out, I convert it to English and I make sure that it's tracking with my brain, and that'll help you guys to memorize it and it'll prevent you from making mistakes. Okay, so you're not really going to be asked to prove a whole lot of stuff in this class. This does prove, like this does prove what's being asked to prove, but this isn't what's considered a classic proof. So when it comes to trig problems, you're kind of doing there's a lot of blind faith math going on because you guys have not been taught or expected to understand what is going on behind these trigonometric identities that you've had to memorize. And so basically what we're telling you to do is to just believe something that someone did in their office years ago. They wrote the proof out, they did all the math, they proved that it's true and that it's possible and that this trigonometric identity can be applied in this particular context. And we're not going to get into why it's true and why it's possible. We just want you to know that it's true and it's possible and apply it. So that's why I kind of call it blind faith math when we do this kind of stuff, because I'm the type of person who likes to understand why things happen in order for me to remember them, this is not really an area where that is conducive to that type of learning. And so, and you'll see what I mean. But this is not a particularly bad example of this. This is an example of knowing the relationship between the original trig functions and their inverses. So we're asked to, so this ddx symbol, I've introduced it in recitation before, and I'm sure Dr. Zalecki has brought it up now that we're getting into derivatives, but so it basically means differentiate with respect to the x variable. If we had defined the function cosine of x as being equal to f of x, it would say df dx. Differentiate the function f with respect to x. And it's basically just f prime, or if we had defined this as f, it would just be f prime, just the derivative or the rate of change. So what they want you to do is prove that it's equal to this. So we're going to have to go through some manipulations. And this is what the first step looks like. You have to recognize that cosecant is the inverse of sine of x. So remember, sine could also, so it could be, it doesn't have to be in the denominator. It could also say sine to the negative first x. But this is what works out nicely for these problems. Just to kind of bring it full circle and make sure that you guys have a grasp of all the ways that this information could be presented to you. So now we're going to go ahead and differentiate. Now that we've put it in a form that we're more familiar with. So I mentioned that you should be familiar with the derivatives of the inverse, not the original trig functions, but you can always just do them on your own. You don't have to have them memorized, and that's what this problem is doing. So it's going to be the derivative of the first, which is a constant, times the second, minus the first times the derivative of the second, all over the second squared. So this term here becomes negligible, and it's just negative cosine x over sine of x squared. And so now you think, okay, I've got to get this to look like this somehow. Cotangent is usually, so I tend to gravitate toward things that I'm most comfortable with first. I'm sure a lot of you guys do too. And tangent is something I'm more comfortable with than cosecant for whatever reason. I know what tangent looks like. Tangent is sine over cosine. So the inverse of that is going to be cosine over sine. And I can pull out a cosine from top and a sine from bottom. And then I'm left with negative 1 over sine of x times cosine over sine of x. This is cotangent. And inverse of sine x is cosecant. So I get negative cosecant times cotangent x. And that's how you do a problem like this. There's only two examples of these. I would expect a problem like this on your exam, but the other examples that we've done are all things that I would say will absolutely be on your exam. Except for maybe one. I can't quite remember which one I said may or may not. Okay, so the normal line is something that doesn't always come up. Pretty much everything else that we've discussed thus far in the lesson is something that I would absolutely expect you to be tested on in some way, shape, or form on the exam. Any questions on how I did this problem before we do another example? Okay. All right, so secant of x is going to be pretty much the exact same thing we did before. So secant is the inverse of something that I'm a little bit more familiar with. So what's the inverse of cosine of x? And so I put it in that form, and I'm going to go about taking the derivative. I do want to mention that you shouldn't drop the ddx until you start differentiating, in the same sense that you shouldn't drop the limit symbol until you plug in the limit. It represents a conceptual misunderstanding. And so we keep the ddx until we actually start to differentiate. Same sort of thing. The first term is negligible because the derivative of the numerator is just 0. And then subtract by the derivative of, or subtract by the second half of the quotient rule divided by the denominator squared. Simplifies to look pretty much the same as the last one, except now I can pull out a tangent a lot easier. Not a lot easier, but the tangent's kind of obvious. It's sine over cosine squared. So I'm going to get negative 1 over cosine x times sine over cosine x. So then this negative 1 over cosine x becomes secant of x, which if you remember from one of our earlier problems, the derivative in this case includes a negative. So it's not negative secant x, it's secant x, which is why I say that you should be familiar with these, because you might get to this point and think, okay, it's negative secant x tangent x. What did I do wrong? You didn't do anything wrong. This derivative is just slightly different in the same sense that the derivative of cosine is negative sine, but the derivative of sine is just positive cosine. And I keep mentioning how the more you do these, you'll get a feel for the pattern. That's true with a lot of calculus, but that's why I would say it's helpful to be familiar or maybe have memorized the derivatives of the inverse, the not the sine, cosine, tangent, the cosecant, secant, cotangent, it's beneficial to have those be familiar to you so you can kind of guide yourself through these problems and be comfortable with your answer and not kind of dilute yourself into thinking you made mistakes. Anyways, shakes out to be this. I even made the same mistake that I was talking about. Anyways, moving on to the next one. Find the equation of the tangent line, exactly the same as what we did before, except now we're going to apply the derivatives of our trig functions. And so we get the derivative of the first. I don't need to use the formula. There is no multiplication here. So it's just the derivative of sine x, which is cosine of x, plus the derivative of cosine of x, which is negative sine of x. And we want that at the instant 0, 1. And so we're going to plug in 0 for all x values. So now we're getting to the unit circle, because you got to evaluate these somehow in order to figure out what the value is. This isn't a suitable answer. When it comes to something like this and you've got plug-in values, we want you to find the actual value. We want you to refer to the unit circle and to figure out exactly what the integer or fractional value would be. And in order to do that, you need to be familiar with the unit circle. So basically, the x-axis refers to cosine and the y-axis refers to sine. And so when they ask us to find cosine of 0, we always start out at this right hand, on the right hand side. It goes 0, pi over 2, pi, 3 pi over 2, 2 pi. So 0 and 2 pi are the start stop point. And you can technically go round and round and round. But really you only really need to refer or be concerned with the first quadrant, because if you have this quadrant down pat, then it's just reflecting it over the x or y axis and changing the sign of those x or y values in order to get the right value. So there's only really 2 triangles that you have to memorize, special right triangles. So I'm just going to talk about, I'm not going to spend forever on this because you guys can Google what the other special right triangle is. But for example, pi over 4, so there's pi over 6, pi over 4, pi over 3, and then pi over 2. Pi over 6 is going to look like this, long and skinny. And then pi over 3 is going to be exactly the same triangle, only vertical. And so the values are the same. You memorize the same set of values. But then pi over 4 is a 40, so this is a 30, 60, 90 triangle. Both of these are 30, 60, 90 triangles. So all of their values are going to be different. But this is a special right triangle that is a 45, 45, 90. And so square root 2 is going to be the length of the legs in both cases. And then I believe, I might as well write them up. I believe that it is 1/2. I know it's 1/2. And then I'm pretty sure that the other leg is square root 3 over 2. And then it's the same for the other triangle, only flipped. And then for all of these, the radius of the unit circle is 1 single unit, and it's 1. But that doesn't come up all that often. So that's just a little bit of background on the unit circle. Getting back to the problem at hand, we're talking about finding cosine of 0 and sine of 0. So we want to find the x value at 0 at this point right here, and it's 1. It's the full length of the radius because it's all the way out there. There's nothing, so when it comes to being in between these intercepts, it's going to be less than, or yeah, it's going to be one of these values, square root 3 over 2, 1/2, square root 2 over 2. But when you're on one of the axes, it's generally going to be 0 or 1. So for cosine, it's 1. What is the sine value? What is the y value at 0? 0, because the intercept is right there. It has no height. It is crossing the x-axis. And just for reference, we're used to seeing that look like that. So along the x-axis here, we would have all of the radians in degrees of, or we would have variations of radian. So it would be pi over 3, pi over 4, pi over 6, not in that order. But that's what would be along the x-axis, and we would oscillate from being at a maximum height of 1 or down to -1, 1, -1, whatever, if we were referring to the sine function. If we were referring to the cosine function, which would start up here, then we'd be talking about, we'd be going back and forth left to right. But that is something that I would review more on Khan Academy. We're not going to spend a ton of time doing that because technically that is prerequisite information, although I know not everybody has that kind of stuff memorized still. But I would definitely brush up on that and be able to recognize that the cosine of 0 is just going to be 1. It's that width there, and that the sine of 0 is going to be 0 because there's no height at 0 right here. And so then the answer ends up being 1. And when we plug back in to our function in the same way that we did with the polynomial examples from before, excuse me, it just shakes out to be this. Any questions on this one? No? Okay. All right, so last couple of problems and then I will cut you guys loose. So these ones I find difficult to teach because it's kind of more of the blind faith math. And when I was learning it myself, I had a hard time learning it because I felt like my teacher could not give me the answers that I needed because by nature of these problems, there's math involved that's just over our heads, things that we aren't expected to know, but we're expected to be able to apply. And so we're going to be using the trigonometric identity that talks about the limit as x tends to 0 of sine x over x. And we're going to basically, the way it shakes out is we pull a factor out, and then we evaluate the limit such that it's equal to 1. So starting out, we pull out this factor. It feels kind of nonsensical, but this is the kind of problem that I would definitely practice. Not going to be a ton of problems like this on your exam, but there may be 1 or 2, especially since it's being introduced in the first recitation of the new unit. So then, again, I don't have a great explanation for why this works out the way that it does. You pull out the factor. Once you pull the factor all the way out, what the end goal here is to get the variable on top and bottom equal. And so and this is the way that the textbook sort of represents that it's the sine x over x. To simplify it, you don't need to use this theta tending toward, you don't need to do any sort of substitution really. But the way, I don't think so at least. I should make a note to double check that in case that's not true. But since the definition, the trigonometric identity that we are using tells us that when the limit tends towards 0 of sine x over x is equal to 1, we're able to pull that factor out and multiply it by 1. This is something that I've seen more as a multiple choice problem than I've seen as a written out problem, which is probably why I have a harder time teaching it, because I really haven't had to put too much mental effort into coming up with a great explanation for it, because more often than not, you really just have to recognize what trigonometric identity is going to be used and then just be like, okay, it's just going to be the factor 5, 3, because I know that it's just going to end up being equal to 1. So this is the type of problem that I would definitely practice, but it's not, I would expect it, I'm not promising you this, but I would expect it to be a multiple choice problem and that you wouldn't be marked down points for not doing the proper string of calculations. So next example, pretty much the exact same thing. So we're gonna pull out a factor, and I think I did a better job of doing it all in one step in this one. I think it's a little bit easier to wrap your brain around. But we get sine of x over x multiplied by that factor, and then by limit law 4, I believe, we're able to break up those two limits. We evaluate this limit as being 1. We evaluate this limit as we do all other limits. We just plug in the 0. So then it just ends up being 1 times 3 over 5 times 0 minus 4, which is just 1 times negative 3/4, which is just 3/4. And that's how you do these problems. And I apologize that if you were, I don't think that these have been introduced to you yet with Dr. Zalecki. So I apologize if you aren't feeling super confident about the way that I've taught it to you. I told the first recitation that I would look for a resource, maybe a video or something to send along with my recitation note, but know that since Dr. Zalecki hasn't brought it up yet in lecture, since he's given it to me to review, you can pretty much count on him bringing it up at some point. It's not typical for him to expect me to do the heavy lifting as far as explaining things. Recitation is supposed to be like secondary. You've learned the material. Now you get to ask questions. You get to learn about it from the perspective of a student themselves, or from a student who's taken this class. So you'll get a brush up on this with Dr. Zalecki. But if you feel like you don't understand what's going on, that's okay, because I don't either, because I didn't sit around in an office and write a full 3-page proof on why this trigonometric identity works. And so I'm not going to understand all the inner workings of the problem. I'm just expected to be able to apply it. And that is the end of my lesson. Does anybody have any questions? We're technically at the end of time, but that doesn't mean that I can't hang out for a couple minutes. Where is I'm gonna stop share. There we go. Anybody have any questions? No? Okay. I mean, there usually aren't many questions the first week after an exam, and especially since this is a lot of formula-based applications, I was kind of expecting that. But I will cut you guys loose. You guys can head on your way. I think there will be a homework assignment due next week. There is not one due this week, though. I will talk to you guys later.
Thank you.
Thank
Yeah, no
you.
problem. Bye, guys.